everyone. Thank you for joining the first webinar of the Reframed Tech Series. It's presented by Pembina Institute's Buildings and Urban Solutions program. Hopefully the sun is shining wherever you are. My name is Betsy Agar. I'm a senior analyst at Pembina, and I have the pleasure of moderating this session. Pembina is a national nonprofit clean energy think tank. We have offices across Canada. I'm here today speaking from Vancouver, the traditional lands of the Tsleil-Waututh and Squamish nations. We work on policy in the areas of renewable energy, the clean economy, oil and gas, buildings, and transportation. I want to thank our funding partners, Natural Resources Canada, CMHC, and the Federation of Canadian Municipalities, as well as our supporting partners, Real Estate Foundation of BC, Sitka Foundation, and the North Family Foundation. As I said, my name is Betsy Agar. I'm a senior analyst with the Pembina Institute, and today I'm joined by my colleagues Stephen Hoy and Ghazal Ibrahimi, who are here helping to ensure today's webinar is a success. Stephen's producing this series and leads our communications, and Ghazal is also a senior analyst on our team. Today she'll be helping facilitate the question and answer period. Today's agenda is pretty simple. We'll start with some introductions. I'll talk to you a bit about our retrofit program and introduce you to our speakers. Then we'll quickly move into their presentations and follow up with a Q&A period. Finally, I'll leave you with the information about an upcoming demonstration project opportunity. So just a bit of housekeeping. Just want to let you know that this webinar will be recorded and will be published online. So you'll be able to watch it later and share it out to others who might be interested. All the participants are muted. And so if you want to ask questions, we'd ask you to type them into the questions box on the GoToWebinar panel. And we'll try to answer as many of them as possible during the Q&A after all of the presentations. So it's my pleasure to introduce you to Pembina's Reframed initiative. Through Reframed, we're working with designers, builders, owners, financiers, and policymakers to scale up deep retrofits. We believe that by bringing all of the players together, we can accelerate and improve retrofit, and we can address our housing crunch and the climate emergency at the same time. The way that we think about deep retrofits is that they are healthy space. They can create healthy spaces out of our existing houses. They are resilient and they protect their occupants in extreme weather and seismic events, and they are low carbon. We recognize that scaling up retrofits is not going to be an easy task, and we have to keep these goals in sight. We need to be keeping rent affordable. We need to minimize disruption to tenants, and we need to do this in a way that returns value to the owners and investors. So to help get everyone on the same page, we've created a primer for today's topic. Hopefully you had a chance to read it before joining us today. It's available now in the handout section of your GoToWebinar panel. This is really just a glimpse into the prefabricated panel solutions that we're going to be discussing today. And we hope that it'll whet your appetite to learn more about prefabricated panel retrofit solutions to take on more of this industry transformation. So I'd like to introduce our speakers. First off, we'll have Jeff Armstrong, who's principal of Cold Climate Building. Jeff has been designing and building energy efficient buildings since his days as a carpenter in the late 1970s. With degrees in architecture from Ryerson and McGill universities, he has been a leading edge designer, builder, and teacher for over 30 years, including 13 years as a trainer for CMHC International. His former construction firm, DAC International Inc., exported prefabricated wood frame buildings to the Canadian Arctic, to Japan, the UK, Ireland, and the US. Jeff now heads Cold Climate Building Inc., a consultancy with a focus on deep energy retrofits and northern housing. Since 2016, Cold Climate Building Inc. has been exploring the use of prefabricated panels in deep energy housing retrofits. As a consultant to NRCan's peer research project, Jeff contributed to the success of the initial pilot completed in 2017 and has since worked to refine and extend these panel designs and techniques to larger scale projects. Want to wave hello, Jeff? Following Jeff, we'll have David Arnott from TAG Panels, who joins us not far from me in Squamish, BC. David is one of 3 co-founders of TAG Panels and is the principal at Stark Architecture based in Squamish. He is registered as an architect in both Alberta and BC, as well as being a certified passive house designer. His background in architecture begins in Scotland, where his thesis was based around prefabricated architecture. David's early designs were small cabins and renovations, always with an emphasis on over-insulation and using the highest quality parts where available. An underlying interest in prefabrication, manufactured timber assemblies, and passive house design from the cold northern climates further influenced his designs. And early ventures in CLT and wood fiber began to shape subsequent designs and create a path forward for the firm. Establishing a manufacturing company to achieve the needs of high performance architecture is a natural progression of integrated design and empowering people with choice. Hello, David. And finally, we have Michael Dombowski of Nexi Technologies. He'll connect with us from Moose Jaw, Saskatchewan. So we really have a cross-Canada panel here. Michael is a prolific inventor and developer of building products and systems with a passion for sustainable structures and sustainable living. Most notably, Michael is the inventor behind the Nexi whole building solution. For over 40 years, he has designed and built projects from custom residential to multifamily, commercial, industrial, and institutional buildings. During that time, he has also manufactured the structural steel and precast concrete for this wide range of buildings. A notable accomplishment was the design and construction of the tunnels of Moose Jaw, a national award-winning tourist attraction that has boasted over 2 million tourists from all around the world over the last 10 years. Hello, Michael. We're all planning our trips to Moose Jaw now mentally.
You're welcome to come anytime.
All right, with that, I will welcome Jeff to the screen.
Just get the presentation up and running. Here we go. So I'm going to talk a little bit about some work we've been doing in Ottawa over the last 3 or 4 years. About 3.5 years ago, I was hired as a consultant by Mark Carver and his team at CanMet Energy, which is a division of Natural Resources Canada, to assist them in their research into the use of prefabricated panels for exterior retrofits. What you see on this slide is a pilot project that we did in late 2017. And that pilot was pretty simple. We took essentially a construction trailer, about 12 feet by 40 feet, and we applied 2 panel types. A nil-base SIP panel. A nil-base panel is one with only a single layer of structural sheathing on it, and a wood frame panel. And we chose these 2 panel types because they're readily available in the marketplace, and our thesis was that if we use products that are already in place in the market, we're likely to encounter less headwind from the industry as we move toward industrializing the retrofit process. So, pardon me, our research questions were really these. We're interested in the whole business of building capture. Building capture is essentially getting as-built dimensions for the existing building, and methods include things like 3D laser scanning, photogrammetry, traditional surveying, that sort of thing. We wanted to know if it was feasible to go over top of existing cladding. The promise of that is that you can reduce cost and time and landfill. And the concern is that we might be baking a problem into the solution if we leave the existing cladding on. We wanted to explore whether or not the air leakage detailing that we had developed for these panels was working properly. We were concerned about hydrothermal performance, and so we instrumented this retrofit so that we could see what the actual performance was and how it compared with the model performance. We wanted to know a few things about buildability, panel handling, and cost. I mean, even though this was a small sample, we're very interested in knowing if there was a clear winner in terms of cost between the two panel types. Let's see here. There we go. One of the organizations that was following this research effort was Ottawa Community Housing. They're a very large social housing provider here in Ottawa with about 15,000 dwellings in their portfolio. They take a total cost of building ownership perspective to their portfolio, which means essentially they think deeply about maintenance costs and the cost of energy. They have many poor energy performers in their portfolio. They have buildings that are many buildings that are over 50 years old that are similar to the one in this photo, low-rise Part 9 wood frame buildings. And working with Dan DeCare, the Energy and Sustainability Manager at Ottawa Community Housing, we decided that we would take one of their buildings, this building in fact, and use it as a second pilot opportunity. And that little checklist at the bottom is an indication of the kind of things that we were focused on in selecting a building from their portfolio. One of the, I'll just point to a couple of those things. This building has fairly large windows, which will come into the discussion a little later in the presentation. It has good solar orientation, which was important because we set out from the beginning to make this a net zero building. And so we wanted to have roof-mounted PV on the building, and orientation became an important consideration. The thing that is really unique about the second pilot when compared to the first is that we had a very narrow research focus on the first. We were only looking at above-grade panels, where the second pilot is truly a real-world project. Indeed, it is concerned with above-grade wall panels, but it includes all these other things as well. The last item on this list, occupants, I want to pay special attention to because particularly with respect to social housing, it's very important to take the occupants into consideration. One of the things that attracted Dan DeCare and his team to the research we were doing at Enercan was the notion that this deep energy retrofit could all be done or largely be done from the exterior. And that held the promise of minimizing disruption to the occupants. Moving along on that same theme, on the left of this slide is an illegible list of all of the steps that it takes to do a project like this. And it's not even a complete list. You see a bit of a blow up there in the middle of the screen that focuses on the preparation of the existing building. And the point of this slide is to really illustrate that these are unique construction projects. We talk about panelized retrofits and the emphasis is on panels, but as it turns out, panels and all of the work that's done off-site is a relatively small component of the overall project. Again, I'll pay particular attention to this blue rectangle, which just indicates that that particular activity requires access to the unit. And if you go back and look at the long rectangle on the left, you'll see that there are several activities that require us to interact with the occupants. So that became a very powerful focus in terms of the techniques we were using, the methodology we employed, the type of communication we had with the occupants. And I would say that there's enough about these projects that's different from an ordinary construction project that more than any other type of project I've been involved in, it really augurs in favor of an integrated project delivery process. And that is simply one where all of the key players come together at the beginning in a collaborative way. And there's a sharing of risk, a sharing of information. It's the kind of communication that really enhances the potential for success of a project like this. The problem with integrated project delivery is that it doesn't lend itself well to a competitive tendering process, so-called design, bid, build process. And that makes certain clients uncomfortable, but it's well worth making the effort to employ this methodology with this type of project, in my experience. So going back to panels for a moment, we see a continuum with current methods on the left-hand side of this slide, and factory finished panels on the other end. And this is really a pathway of industrialization. And in order to make the capital investments required to industrialize the process, you need a certain amount of confidence about the size of the market and the business model. But the promise of moving from left to right on this continuum is that you'll be able to reduce the cost of the retrofit and also decrease the disruption to the occupants. So on this second pilot that we're doing with Ottawa Community Housing, we land kind of halfway along that continuum. So as you can see in the photo in the background, there's a small shop which Ottawa Community Housing built for themselves. They felt it was very important to gain the learning that this pilot project would afford. And so they decided to fabricate the panels themselves. So we took base panels, which you can see stacked up there in the foreground. These are SIP panels. And it's work that's going on right now in that shop, where carpenters are taking those panels, properly socially distanced, and adding the various layers that are necessary for a fully finished panel. So air barrier, rain screen cavity, exterior cladding, windows and doors, those elements are all being added to the panels before they get delivered to the site and installed on the building. And there's a couple of shots of the shop just to give you an idea of the simplicity and the scale of the shop. This need not be a very large capital investment. It's a fairly modest facility, but and it's one that can be scaled up as the scale of the opportunity increases. A couple of other things that OCH did is they had built some racks to store the panels on site and to transport them there. They have a certain amount of equipment that they own themselves. This is a small telehandler that they use for loading the panels on those racks and moving other material around on the site. And it's their intention to lease a rotating telescopic forklift, a bigger one, to install the panels on the site. I'd like to move now to the last subject that I'm going to cover in this presentation, which is the whole idea of panel fit strategy, which is a term we coined in the research phase of this project. And the idea is that there are a lot of dimensional issues that you need to take into consideration if you're going to fabricate something off-site, bring it to site and hope that it fits. So starting with the materials out of which the components are made, they have a certain dimensional tolerance that's acceptable within, the standards of that manufacturing process. There's the issue of panel creep. Anybody who's worked with panels knows that if you add panels together, panels of a known dimension, by the time you get to the end, you get a dimension you didn't expect. So panels tend to grow. So that's another factor. There are workmanship tolerances. There are anomalies in the base building. Things, as everybody will know, are not necessarily square or plumb. And when it comes to the building capture process, if you're using photogrammetry or laser scanning, you end up with a digital point cloud that has to be converted into something that a panel designer can use to do shop drawings. And there can be assumptions made in that conversion process. There can also be building capture inaccuracies. So we were very interested in that last point, given that part of our research mandate was to compare different building capture methodologies. And I'll give you an example of what I mean. What you're looking at here is, in fact, a point cloud of two elevations of the second pilot building. The architects who provided us with that point cloud data and are very experienced with that kind of thing, and they were responsible for converting the point cloud data to the drawing that you see now, which is a two-dimensional drawing with all of the important dimensions clearly indicated. But in the spirit of the research that we were doing, we decided to compare that point cloud data and the drawing that came from it with another data set that we got from a surveyor who took a total station out to the site and, armed with this drawing, gave us the dimensions that are indicated here. And we were very interested in comparing those two, just to get a sense of the reliability of both data sets. So the surveyor gave us a drawing that looked like this. We had the laser scan data that produced that, and we cleaned them up and overlaid them on each other. And you can see the kind of discrepancy that occurred. It surprised us a little bit, 51 millimeters is about 2 inches. And so, again, with reference to the issue of panel fit, this was an important realization that regardless of how much effort and energy is put into capturing the as-built data, you need a strategy with respect to panel design that can accommodate a certain amount of error. When it came to windows, I think this was probably the worst window we had. It's about 1.25 inches of difference between the two data sets. So this is a vertical section through a window. I mentioned earlier in the presentation that this building had quite large windows. So we had the luxury of making the windows in the new panels a fair bit smaller, which is a way to accommodate the discrepancy in the building capture data sets, but any other discrepancies related to building material tolerances, et cetera. So that was part of our panel fit strategy, was to make the windows smaller. The idea is, as we get more confident and do more of these, we may be able to shrink those numbers quite a bit. But in the early going, we're erring on the side of being conservative. This is a horizontal section through a joint where two large panels come together. And you can see we've given ourselves quite a bit of tolerance there so that the panels can be slid to the left and right. And the joint between them has a compressible foam in it that allows for a significant amount of movement without losing the thermal properties or the air leakage properties associated with that joint. A third thing we did is we intentionally created a corner panel, because at the end of an 80-foot long elevation, if the panel is sticking out a little further than it should, it's an easy thing to adjust the corner panel. It's an easy thing to cut, and adjustment of that sort can be made. So these are elements of the panel fit strategy that we employed. Even on the vertical dimension, we had, of course, vertical dimensional data from our building capture process, but we created a little bit of room for the panel to grow up into the soffit if it needed to. And finally, my last point is that many of our panels had both windows and doors in them. The most important thing when setting the panel is aligning the door, because doors come in standard sizes, whereas windows come any size you want them to be, assuming they're fiberglass or PVC windows. And so by making the windows a little bit smaller and making the door a standard size and positioning the door against the existing door opening, the windows effectively fall where they do, but they're assured of lining up with the openings in the existing wall. So that's just a bit of a flavor for the sorts of lessons that we're learning in the early going on these pilot projects that we're doing here in Ottawa. And with that, I'll hand it back to Betsy.
Thanks so much, Jeff. That's a great overall view of what you're doing in Ottawa. So I'll pass the mic on, so to speak, to David.
Hello, hi, yeah. So I'm one of the 3 co-founders of Tag Panels based in Squamish, BC. So in a short period of time, I'll talk to you about 13 years of interest in prefabrication. For today's presentation, I wanted to focus on 3 key points, as I believe these are most relevant to the Pembina Institute work on prefab, as well as being of interest to our audience today. These 3 points are: what are tag panels? What are the materials and embodied carbon in tag panels? And how can prefabrication benefit new builds and retrofits? So as I said, I'm David, co-founder, registered architect in BC, certified passive house designer. My other co-founder is Brian Gavin. He's a prolific contractor in the sea to sky. And Ben Towsey, a registered structural engineer in BC. We like to think our secret sauce, so to speak, is having 3 very specialist interests and bringing them together in a company. Here's a quick shot of some of our team. We're carpenters, modelers, operations, productions, all with a shared passion for high performance building. So I wanted to start with a quick refresher of where we are today and where we've come in the last 30 years. And if we are doing retrofits, are we building a better system? And if we're replacing an envelope with a marginally better system, are we in danger of repeating our mistakes? So here are 3 buildings, all in Vancouver, spanning from the 1930s to the 2000s, one of which is a LEED certified building. And it'd be a guess for everyone to guess what the average R value of that assembly is in that wall. And so it'll be surprising to everyone that all 3 buildings are somewhere between R2 and R3.5. So it's very important when it comes to retrofits that we are making a better system and that we're upping this, as opposed to not merely making them look good or kicking the problem down the road. So back to our first point, what exactly are tag panels? They're prefabricated, sustainable building panels used in construction which can help clients achieve high performance goals. We started the company with a series of typical build-ups, allowing us to meet various levels of the step code, as well as passive when combined with air tightness. Here's our typical panel here, which shows a sort of 2x8 timber wall filled with blown cellulose insulation. We put wood fiber on the exterior. We put a high performance WRB on that exterior. The inside vapor retarder is actually OSB or plywood, which is then taped. And then inset from that, we would have a service cavity. But we don't believe in a one size fits all. And all our panels can be customized for the user. Usually we work back from an energy model or architectural specification for required R values. So here's an example of a Larson truss system we are modeling for a passive house client. That's with TGIs on the outside filled with blown cellulose, and then a structural service cavity on the interior. This is our smaller location. We're currently moving into a 10,000 square foot location in Squamish, but this was a great opportunity for us to test and be a little bit more efficient with our storage and spaces. So we've got some good new practices to take to the larger location. Each panel is built flat on the table, flipped by an overhead crane. filled with blown cellulose, stored ready for transport. Panels are built in reverse order, and even the tractor trailer loading is modeled to ensure the efficiency of the stacking, so we're reducing the amount of trips that we make. So going through the process a little bit, we start with the client's needs in terms of build-up, insulation value, or budget. We then 3D model the entire project, including every stud, joist, beam, insulation, and sheet of plywood. So this is really key in our process of allowing us to integrate and coordinate the structural elements and critically provide accurate pricing. This model is then turned into 2D shop drawings, which are dimensioned with cut lists for each panel and outputted to the factory in the order that they are to be built. At this stage, we would have the structural engineers sign off on the shop drawings. We take pictures of the panels. So this reduces the need for the structural engineer to visit the site. Fabrication then takes place. Typically, we're finding a 3,500 square foot home takes roughly 20 days to build within the factory. Installation is the next step, taking between 5 and 10 days for a 3,500 square foot house. Our second point is the materials used and their benefits, as well as their ability to capture carbon or be smart carbon. We're aware of the growing trend in insulating, but not at any cost, especially when the question is asked, how much carbon did we emit to save X amount? The materials that TAG use actually store carbon and compare favorably with XPS, spray foams, and the largely petrochemical group of insulations. We're big on sustainability and recycling. The materials we use also serve dual functions. As the air barrier is so crucial in any assembly, we're giving ourselves the best chance by having the plywood, the wood fiber, and the membrane act as an air barrier. We also construct that plumbing or service wall inboard of the interior plywood membrane, so that removes all the cuts and penetrations typically associated with the standard wall. We don't install our roof membrane with waistcoats like this guy though, we've not got to that stage. And then vapor diffusion. So this is a big thing for us. It's the breathability of the panels. It's fundamental to TAG. Having your envelope airtight but breathable allows moisture to dry inwards or outwards, especially important in retrofits where existing structure may need to dry outwards. So let's stop trapping moisture. And then so for these last couple of slides, I'll go through some of the benefits as we see them. We obviously believe that there are dozens, but related to retrofits and new builds, I wanted to highlight 5 main points. First is the actual construction. So building your high performance investment in a climate controlled facility with the materials for the most part people are familiar with. You don't expect your high performance expensive Audi to be built outside. So what about your high performance home? The second reason is, conflict resolution. Jeff mentioned this as well, but we talk and hear a lot about integrated design, but with prefab, like he says, your hand is forced and you truly have to coordinate the design on a computer and not on a site months after a job has started. We've seen incredible benefits with structural coordination. No matter how many times an architect or a structural engineer claim to coordinate, once it's drawn in a 3D model, it is truly coordinated. Fixed price. It's a bit of a shocking phrase in the building world, but again, you wouldn't order high performance windows in pieces and have someone put them together in the rain at an hourly rate. So why not fix one of the largest line item costs in your project? Time. So no more linear time charts. Your weeks of demo or foundation forming are now usable time for the panels to be built. Windows are ordered during the modeling phase and lockup happens much faster. And finally, performance. So we need to stop taking chances with high performance. When builds rely on airtightness and insulation values, specifically for code requirements, having certainty over this is paramount. No more trades coming through and ripping holes in vapor barriers or missed beams having to be placed through exterior walls. There is an ownership of the envelope with prefab, which is very important. So whether a retrofit on an aging apartment or a new build, we feel prefabrication will be of benefit. So in summary, TAG panels, prefabricated, sustainable, vapor open, high performance building panels. The materials are a mixture of timber, wood fiber, cellulose, and high-performance membranes, which help reduce embodied carbon. And some of the benefits are controlling those building conditions, removing the conflicts early on, providing a fixed price, reducing on-site time, and helping to achieve significant performance over traditional systems. Yeah, we have more info on our website along with our blog. So if you have any questions, feel free to reach out to me. So we're just big believers in a rising tide lifting all boats. So as long as the future is prefabricated and sustainable, we're here to help. So I'll pass it back.
That's great. Thanks, David. Already we can see some different approaches emerging, so appreciate your thoughts on the materials selection. And with that, I'll switch over to Michael.
Well, thank you. So Nexi Building Solutions is kind of the new kid on the block. We have developed an innovative new way, patented and patent pending, building system, both for new build and for retrofit. In the retrofit world, and just bear with me, waiting for a slide change here. And having an issue with that. My apologies. So here we go. In the retrofit world, you have an existing building. And I should say in beginning that our approach is presently gearing more and more of my presentation is about larger buildings. So what we're creating is a cocoon over the existing building, both wall panels, foundation panels, and roof panels. And like a museum, everything inside the existing building is encapsulated within that new building envelope that is airtight and watertight. So the Nexi technology, what we've invented is a new way to build buildings. Plant fabricated, and these panels are finished both on the exterior and the interior. In our retrofit approach, our panels are not structural panels. So we're allowing and using the existing building to do the work of carrying the load of the panels. The panels have an exterior skin and an interior skin of a cementitious material that we call Nexite. The core of the panel in retrofit is GPS, styrofoam with graphite in the product, which allows us a higher R value of 5 per inch. Around the perimeter of the panel on the inside is a structural frame, and that frame can either be Nexite with reinforced steel, or it can be a HSS or steel members that allow us to crane the panels, lift the panels, and attach them to the building. Every panel has corner blocks of metal that allow the panels to be lifted and attached to the building. And they are steel components, and it allows us to bolt the entire building system together. The net result are panels that, as I said, are plant fabricated. They're finished with the exterior finishes on the panel, fully insulated, and the interior on a new build is paint ready. On a retrofit, that interior surface is fire rated, and it's the gap. There is a gap, a 3/4 inch gap between the existing building and the new building. By the time the building system is buttoned up, it's airtight and super energy efficient. Our first retrofit project was done 4 years ago in Musca, my home city. This is a 5-story building, and there were 30 panels on this building, and it took 30 hours to install that new wall on the back of the building. In this particular case, the old wall was removed and the panels were installed over the empty wall, the empty space. Typically though, in retrofit, our approaches that we're working on for the new projects, people are still living in the suites and the retrofit panels are going over the existing building. With these 30 panels, they were 12 feet tall and 9 feet wide. And I'll address the size constraints that we have in our present casting process in a future slide. So here we have a commercial example of a building. So this is going to be a new build, a Marriott hotel out in BC, out in Nanaimo. I'm showing this slide because I'm demonstrating that architects in creating a new aesthetic for a retrofitted building have no limitations. You can create, any aesthetic, and I'm going to show you later the numbers of finishes that we have. But what it's allowing when you're doing a retrofit is a significant upgrade to the value of the building, the longevity and the value of the building. So the number of panels in the building system, we have foundation panels, foundation skirt panels that wouldn't go all the way down to the footing, and other panels that can take you all the way to the footing. It depends on the energy modeling and the goals there. We have corner panels for wall panels, and then standard infill panels that take you along the building. So corner panels are a blunt corner teeing, or rather going at the 90 degree. We have parapet panels and then roof panels. So our project that we are working extensively on right now in the planning stages is Eva White in Boston. It's a 5-story building, and we're modeling presently, and you're seeing here a slide where we're working on the schematic design. In the schematic stage, we're solving the issues and supplying this information to the architect of record. The key aspect to putting panels onto an existing building, we typically want to bear this panel or hang this panel from the existing building from 2 points only. And that's important in working with the engineer of record to determine that the base building can take the loads that we're going to apply. Here I'm showing a 2-story low-rise wood frame building that, again, a retrofit scenario. We're working with Rocky Mountain Institute and the California Energy Commission on a retrofit. And in that scenario, it is wood frame as compared to the previous example I was showing with Eva White. The challenge in retrofit, really larger challenge, is how we deal with the foundations and getting the insulative material down below grade to maximize the thermal efficiency. As you'll see in this slide, the slide on the left, or the detail on the left, has the roof trusses that were actually added to the building because it's a flat roof building presently. The tails on the roof trusses have to be cut off because the new panels that are going to go over would interfere. So that's what would happen in a retrofit, is the roof overhangs need to be cut off in order to put the new panels over. As you can see here, I'm integrating solar PV right into the roof panel so that they're flush with the roof surface rather than sticking above the roof. So in design, we begin with a 3D survey of the building, point cloud survey. We then go on to schematic design of the panels. And this is really driven from the architectural drawings, and we need to work with the architect hand in glove so that it reflects the desires of the architect. We do full 3D modeling of every panel for the entire building. And so that point cloud scan is going to identify where there are potential conflicts. So the engineering of the hanging system is very much critical point at this stage. And then we produce the full shop drawings. And that takes us into production. And in production, we use processes of automated manufacturing. And I'll show you more of that in future slides. Typically, we're looking at 12 to 24 weeks in planning for in production. 2 weeks in installation and 2 weeks in completing the seals between panels. We are not, Nexi is not a general contractor. We work with a general contractor, and they would take care of the millwork inside and all interior renovations. The installation, however, is under Nexi's umbrella in that we have certified installers for the Nexi panel system. In our project delivery, we begin with the production of the tracks and then go on to the production of the panels with the windows installed into the panels in the plant. The panels are transported to the site vertically. Before the panels are taken, though, to site, after the track system is installed on the building, we'll do a point station survey to confirm that the hangers are all in the correct locations. Then the panels are installed, and that's actually a very quick process, putting them onto the building. But sealing them up takes as long as it does to put the panels onto the building. So our design constraints: panels are 10 foot tall, 24 feet long. Roof panels are the same size. Our panel weight, 10 pounds per square foot for wall panels. That includes the windows. And now as I said, our 5 per inch. The roof panels, our target weight is 5 pounds per square foot. So some of the challenge in retrofitting existing buildings, especially on larger buildings, is we need to deal with the protection of the base building as we're creating a building envelope. And in that respect, we need to put in fire seals at the top of every panel and at where a suite ends. And that's dealing with fire, smoke, sound. That also would then affect the air quality. We're not allowing odors to pass through. Our design targets are Passive House standard for insulation and air tightness, and our building panels and retrofit is net zero and net positive ready. The pricing is presently $40 to $50 a square foot on wall area, and that's at the pilot stage. We believe that there's the potential to get the pricing down to the $30 range with scale. So everything in the way panels are made, it's all plant fabricated, and we use a whole ISO 9001:2015 process of inspection, whereby everything that we're producing in the plant will reflect what's on the shop drawing. Exterior finishes, we have many exterior finishes. Our least expensive exterior finish is a mineral coating that's similar to a paint. Keim, a German technology, has been around for over a century, and these are color-fast materials that'll last for 50 years. We also put on a trowel-on in the plant finishes that you're seeing on the left of the screen. They're like an acrylic stucco. And we can put on brick face, thin quarter-inch thin face brick. We can cast finishes right into the panels, which will give wood grain and reliefs, as you're seeing in the 1912. And this final slide, this is a demonstration project we have in Squamish, and that's an example of our exterior mineral painted exterior finish. And with that, I'm completed.
Thank you so much, Jeff. I asked these folks to try to summarize all of their insights in, under 15 minutes, and I think they did excellently. So I'm also seeing lots of really great questions coming into the question box, so it's great. Okay, so thanks to all our presenters for paving the way to our this discussion. I think we'll kick off with a poll, just to see if everyone's been paying attention. So in what we've heard, what are the biggest advantages of using prefabricated panels for building retrofits? Numbers are rolling in. So 2/3 of you have answered. All right, looks like we've slowed down here. So from what we heard today, it looks like people really heard that the minimizing disruption to occupants was a real benefit, higher quality construction. Next came in less demolition and construction waste, lower risk of costly construction delays, and less demand on an already stretched labor force. So these really highlight some of the benefits of prefabricated solutions in not only new buildings, but also in retrofit solutions. So to start us off, I'd like to start with a question about how you're considering trade-offs. So it's clear that you all have unique panel systems. You're approaching it in different ways, using different materials and methodologies. And I just wonder if you could each highlight a little bit, what are the considerations you're making when you're making those decisions and trading off between those different parameters. I think David's muted.
Yeah, if I start, I think one of the biggest trade-offs that we have to make is that our panels are so customizable, which is actually a problem. We don't, it's every project we start from scratch and we can fully customize those panels. So I think that would be a trade-off. Having some sort of standardization, I believe, will help with retrofits. So that's one of the trade-offs we have.
Go ahead, Jeff.
In terms of trade-offs, you mean for a systematized approach versus a kind of a site-oriented approach? What sort of trade-offs is that?
Yeah, and then how you're coming, and the systems that you choose. I've seen different materials adopted. So David talked about embodied carbon. Michael mentioned weight and costs, and some of that decision making around those decisions.
Yeah, I think that a lot depends on the objectives of the client and the rest of the project team. The structural engineer, for instance, is going to have questions that will influence the choice of what materials get used to a certain extent. The building condition assessment, like the condition of the existing building, might favor one approach versus another approach. What the overall energy performance target for the building is there going to be on-site renewable energy generation as part of the equation? Is there fuel switching involved? So all of these factors can influence the specifics of the panelized approach that you take. So again, it's very important to bring people who have an opinion on all of those various aspects together at the beginning and very quickly distill out an approach that seems to cover off the concerns that everybody around the table has. And I think that in terms of, from our perspective, from a research perspective, in terms of the choice of panel type, I think there's, we're not wedded to one particular panel type versus another. I think there are many different panel types that could be used very effectively depending on the particular circumstances. So that's good. And as this market develops, presumably there will be more people in the market with various solutions and more to choose from. So I think you can craft a customized solution for each project. And but once you've got a building owner like a large social housing provider, what you'll find is that over the first couple of projects, the number of variables gets winnowed down, and you begin to go with the team that's been in place, you go with the products that have been in place. But in the early going, it may take some experimentation to get that right mix of elements.
As for Nexi and the trade-offs, we've chosen to use EPS and GPS as our insulative core. And our Nexite, between the EPS and the Nexite, there is higher embodied carbon than a wood-based solution in a cellulose fiber. However, again, we've chosen to use the EPS as that insulative material and the Nexite because that's the building science that allows us to plant fabricate panels that are resilient, that have a 150-year lifespan, that there's nothing in a Nexi panel that can biodegrade. So there is a trade-off, right? You're saying has a little higher embodied carbon than a wood solution. However, there's the trade-off is a positive one in our opinion, whereby it allows us to plant fabricate. We can make them really fast. I mean, the beautiful thing about the technology is how simple the labor process is in making a panel. And so our studies have really pointed that it's the longevity, the speed of construction, the fact that they are plant finished in every respect so that when they crane in place, they're done, that those gains are greater than the cost of the non-EPS solution. So it's a less than perfect world. These are the materials that our system is based on, but we believe the gains are more than the expense.
Great, thank you. I'm going to give a question from our audience. Curious about the SIP panels in Jeff's presentation. Sorry, that just moved here. What is the insulation specifically? And raising a question about foam and the environmental impact of foam in making that choice.
Yeah, the embodied, well, where to start? The embodied energy in the foam, the cost of that embodied energy is paid for very quickly in energy savings once the panels are in place. Foam has other environmental characteristics that are less than perfect. EPS is less of an issue in that regard than, say, extruded polystyrene, which has blowing agents that have a higher global warming potential. EPS uses a blowing agent that doesn't have a high global warming potential. But our choice of panel, we trialed in our initial pilot two approaches. One, the wood frame, the other, the SIP. The wood frame used blown cellulose insulation that was installed in the field. We decided to go forward with the EPS panel for the second pilot because we had more confidence in just how continuous the insulation would be when compared to the other approach that we had taken, which involves site-installed cellulose. The other thing that we were very cognizant of, and this is a very practical consideration, is what the building department would accept. To the extent that you are promoting an approach that is very unfamiliar to the building department, you can encounter a lot of resistance to what you're trying to do, and that can have a very real impact on the project schedule and the cost of the consultants and everything involved in convincing the building department that it's a reasonable approach. So that was another reason we chose the EPS solution for the second pilot. And we used a panel that had CCMC approval, and that was very important to the building department. So that just illustrates the kinds of considerations that you might not think of right away that can have a very real impact on the choices that you make.
Right. David, I think this question is for you. Can the wood fiber be used as the WRB or the water resistant barrier if a liquid system is used to detail the opening?
The wood fiber at a certain thickness can act as a WRB. It does have a small amount of paraffin mixed into it. So I have seen applications. We did a house which was a CLT house, which just had wood fiber clad on the outside, and we didn't require the membrane, but it was actually, going back to Jeff's point there, where no building inspector would actually approve that. So we actually had to have an architect or an envelope consultant sign off on it. But theoretically, yes, it can. And in Europe, that's what they do for WRBs.
Michael. Existing buildings need improvements to their seismic performance, not just energy upgrades. It seems like the Nexi approach could compromise the structural integrity of the buildings rather than improve it. So just curious about the choice of the approach and if you have comments on that.
Mm-hmm. That's a good question. And it's one of the things that we're actually going to be resolving in our California Energy Commission project that we're working with them. Our panels are a very stiff panel. And so adding the panels, even though they're lightweight to the building, there are still some considerations that have to be engineered and tested to some degree. So, the jury's still out, frankly, on how that's going to work. And it's very much a studied and engineered solution that we're working for.
Thank you. Jeff, somebody's asking for clarification about what you used for the compressible foam gaskets between the panels and where you found them, where you can get them.
At the panel joint, at the vertical panel joint, we used a polyurethane foam, a very low density polyurethane foam material that's widely available in the construction marketplace here. The other compressible material that I didn't really refer to in my presentation, but plays a significant role in the solution that we developed, was a compressible material that we applied to the back of the panel as well, where the panel goes up against the existing building. And we felt it was important to have that so-called squishy layer in the back so that we could take up some of the geography of the existing cladding, keeping in mind that we're going straight over, in the case of the second pilot, we're going right over brick. So we wanted a material that could conform to any surface irregularities. But more importantly, I'd say we're interested in seeing to what extent that vapor open compressible layer on the back of the panel can encourage drying to the vertical drying in that zone behind the panel. If any moisture manages to migrate out of the building into the new assembly, what is the drying potential that is afforded by that vapor open layer on the back of the panel? So that so-called squishy layer was carefully selected. It turns out it's a form of glass fiber insulation, very low density, but it allows us quite a bit of flexibility in terms of establishing plumb for the panels and fitting with the irregularity of the surface that it's put against.
Michael, I wonder if you have any comments about some of the connections between your panels and managing the topography of the existing cladding.
Our experience thus far is that the existing building varies. It's in and out. There are undulations on the exterior surface, and so we're designing a 3/4 inch gap between the inside face of the Nexi panel and the outside face of the building. Our point cloud scan and our 3D modeling is intended to resolve the conflicts and know when the gap is narrowing. And we're fine with the gap narrowing to less than the 1/4 inch, as long as they don't touch, as long as the two don't rub together. But we are sealing between, as I said, very important to seal between units on multifamily for fire spread and for vapors or odors to spread. So rather, Jeff's point about the continuous insulation is interesting, and something I'd like to have us study more. And I think, the beauty of what we're doing here, this is a collaborative process. There's lots to learn. This is a new field, retrofitting existing buildings. And I love it, that Pembina is taking the lead, as is RMI in the US, and you guys work together. This is excellent to be able to collaborate and learn from each other.
Yeah, thanks for that. I mean, that's really the intention of this, is to start this conversation. We have a question about water. We love water in BC, and water penetration and damage is pretty ubiquitous in buildings older than 20 years. Often the damage is not fully understood until you remove the cladding and conduct invasive exploration. So just curious how you incorporate this reality into the project design and construction process for panel-based retrofits. I'll open that up.
That's something that we've encountered on a project that we're looking at working on in California, and there is dry rot. You find those things, when you begin to do the remediation work, and so those things ideally should be rectified before you envelop the building in a new cocoon. Structurally, I mean, we're asking for the base building to do the work of carrying the load of the new panels, and so validating and verifying that the base structure in the first place has the capacity to carry the load, and secondly that we're not entombing things that have a negative impact on the air quality inside. Typically, though, we believe that the air quality is going to improve when you retrofit the building, bringing it to a net zero or net positive. It will have a new air, a ventilation system as part of the retrofit, and that typically does mean that the air quality will improve because the air heat exchangers the ERVs are going to improve that air quality.
You're making me think about, the ideas that when you prefabricate, you need to be really thinking about the full building system. And so all of you are prefabricators, wondering how you plan for and integrate the systems, the mechanical systems and chases that need to work in tandem with your panels, whether it be new builds or existing buildings.
Yeah, it's to do a net zero building, you're really obliged to deal with mechanicals. Very often these older buildings have no mechanical ventilation other than exhaust fans. And it's an interesting question, the extent to which ventilation ductwork might be able to be incorporated in the new panels that are being applied to the outside of the building. For instance, if you don't have a forced air distribution system in the existing building that you might be able to utilize, how do you achieve the mechanical ventilation that will be required when you air tighten the building? And there are examples of how this can be done from our friends in Europe, where they typically have hydronic systems, radiant heating, and they typically don't have any kind of forced air distribution. So they've been kind of quick to explore the issue of incorporating ventilation ductwork in the panels. So it can be done. We're doing a very small amount of that by incorporating some ductwork in our panels relative to fresh air supply for the mechanical ventilation. So we've got a little bit of ductwork that's being incorporated into our panels to facilitate the fresh air supply for the system. So I think that it's a very interesting area. I mean, it's in our case, in our pilot project, we have forced air distribution, so we haven't had to think that deeply about it, but it is something that I think holds a lot of promise. I think it is possible to incorporate ductwork. And I just quickly want to go back to the previous question about problems with the existing building, you know, moisture problems and things that may be lurking in the existing building. And the approach that we've taken is to do a comprehensive building condition assessment. What that means is you look at the places where problems of moisture ingress are very likely to appear, sort of window sills and you know, where downspouts have been disconnected and that sort of thing, and really get a sense of whether any structural damage has been done to the building over time through water, whether there are any real mold problems that run the risk of being covered up. But once you've satisfied that yourself that those situations are under control, then you everything you intend to do, which is to air tighten the building and raise the temperature of all the condensing surfaces that might be at risk within the building enclosure, you're just improving the situation. And so by implementing standard building science practice to the new enclosure, you're really eliminating the potential for moisture problems to occur. You just have to make sure that there's no structural or mold damage back there that could really come to haunt you.
Yeah, I'll speak to the penetrations and facilitating services within a panel. So we 3D model everything that's going to be in a panel, as David was mentioning as well. We know every single component going in. So we use a complicated software called CATIA by Dassault, and it allows us to fully, you know, model everything that's going to be there. So we'll put chaseways where needed into a panel, allowing us to pull wire if needed. Penetrations for ductwork, for example. We'll facilitate that. We'll actually do that into the panel. What we don't want to happen on site is people cutting into the Nexi and compromising the thermal envelope. We'll put those into the panel with couplers and allow quick connect couplers on the inside of the building. And so we want to take responsibility for penetrations, windows and any penetration in a panel, and the seals between panels are critical to the air tightness and the water management of the system. Something that I didn't say in my presentation is that on the exterior of the Nexi face of the exterior of the building, there's a grid work of channels that are cut into the EPS and an air gap that allows water drainage in the event that it ever gets in. So we build everything and we install it as though we don't want water ever to get in. But what we know about water is it somehow finds a way. Somewhere during the life of the building, it finds a way. And so we create within the panel the ability for water to get out. But joints and penetrations are critical that they be, we believe, managed and you know, in implementation from the plant, from the beginning of the process.
We have a question about the LiDAR. Like some clarification from Jeff about, you know, which measurement you determined was off, and wondering if Michael, you had a similar experience with the precision of the LiDAR results.
What we determined, if you think back to the slide where I showed a discrepancy of about 50 millimeters at the edge of the roof on the left-hand side, what we determined there is that the folks who had taken the LiDAR point cloud and and developed the two-dimensional drawing, pardon me, developed the two-dimensional drawing from it, had just straightened that line out instead of leaving it where it was. You know, in the conversion of the point cloud to a Revit drawing, they just drew a straight line. And it took us a little while to figure that out, but it just underscores the importance of, in our view, whoever's designing the panels should have access to the point cloud data. So if there's a decision of that sort that needs to be made, it's made by the person who's designing the panels rather than by somebody else. So to kind of shorten the chain of people that get to manipulate the data is an important lesson that we learned there.
Jeff is further along than we are in the whole 3D survey world. We, on our first, we've done 2 retrofits. On both of them, they were fully manually measured. In the Eva White project, we're just at the stage where they're doing their initial point cloud scan. And so we've been modeling using other files to basically go through the exercise of you know, the theory and the exercise of using the data. We're just going to be getting into our first here in the next month.
Great. David, we have a question for you about the taping the OSB and whether it's sufficiently airtight when you do that.
Yeah, absolutely. Once you use OSB over a certain thickness, it has an air tightness rating there, and the tapes are airtight. Tesco and Vanna tapes that we use, or there are Sega tapes as well that you can use, so it's completely airtight.
Mm. And the asker has indicated that they've heard of problems with the OSB. I just wonder if you have a sense of when those arise. Is it just the thickness, or are there other factors?
Problems with the OSB in relation to air tightness?
Mm-hmm.
The only problems we've ever come across with the OSB is there are certain clients who tend to not like formaldehyde, and even though there's very small levels of formaldehyde in OSB, and they typically only actually come out once they're wet, that they're a problem. But we have the easy fix. We can shift those clients over to plywood, but we've never had an air tightness problem with either material when it's installed in a climate controlled shop.
There's a question about end of life for particularly this question is about Nexi panels.
Good question. So first of all, we believe that the best end of life is repurposing. So the panels that are, I mean, we from our studies based on the Nexite as an ultra high performance cementitious material, 150 years is a reasonable lifespan for the material. Its bond, the Nexite bond to the EPS, is a covalent or a chemical bond. So there are no adhesives that are going in. And I should say that there are no red listed materials in the Nexi panel. I'll qualify that. 99.9% red list item free, and 0 waste on the job site. And we're actually going for validation or certification of 0 waste in the plant, in the production process. But the end of life, we are developing, because we do a lot of testing of panels. We're developing the methodology whereby the cementitious material is ground off and recycled back into sands and so forth. The EPS, we have leftover EPS when we create a panel. And we have that reground, reconstituted right in the plant, and it's sent back to our suppliers and put back into our ETS. So we're able to reuse the materials. All of the steel components that are in, they're designed, they're machine made, CNC machine made, and have the opportunity to actually be reused in a future panel. But my favorite really is reusing a panel, finding a way to reuse a panel in a new way. They're all bolt together. Take them apart and reassemble them into a new configuration.
Great. We're coming to the end here, but there was a question about costing from Jeff and David. I wonder if you guys have quick answers to that.
How to cost the project?
No, just the cost of your panels. Michael gave us a bit of an estimate, and wondering if you have a sense of the cost per square footage.
Yeah, it's a very hard number to pull out, just because the panels can be so flexible, you know, in the amount of Gutex or the amount of wood fiber that we add. But typically, we're seeing that over the square footage of the entire house, it's around 50 or 60 square foot. So if you, yeah.
Jeff, how does yours come up?
What we're really focused on is the total project cost. And that includes all of the steps that we're taking, including the below grade, the PV, the mechanical upgrade. And I've not been as closely connected to the overall project cost as our friends at Ottawa Community Housing on this first pilot that they're doing. But they have satisfied themselves that the total cost of ownership perspective really supports the process that we're taking, and the costs, even the costs in this initial sort of startup phase for this kind of method, those costs are acceptable to them when they take into consideration the deferred maintenance and the deferred energy cost. And when they compare it to the cost of tearing a building down and building a new one and finding places for the occupants to stay because they have a 10,000 person waiting list. And so in terms of the total project cost, even in this sort of pilot phase of the process, they've satisfied themselves that it makes economic sense to them. And that will only get better as we all become more efficient with what we're doing, including, you know, the various aspects of the supply chain, and contractors become more familiar with the process and all of that. So the costs are going to go down. But even now, according to Ottawa Community Housing, it makes economic sense for them to go this direction.
Great. I think that's probably a pretty good note for us to wrap up on. So, you know, lots of questions still on how we need to be thinking about prefabrication and the role of retrofits, and when a building configuration and the articulations in a building, when does the building make sense for prefabrication, or if that's even a limitation. And you know, we deliberately selected people from different streams. You know, David's a prefabricated panel manufacturer and also does retrofits separately. You know, how do we bring these fields together? Michael's coming out of a modular housing perspective. Jeff's been retrofitting for years and also has had prefab history. You know, would love to be able to continue to tackle this and you know, really consider what the industry needs to be to working on to start to bring together all of our knowledge. So appreciate everything you've done here today to talk about bringing that together and sharing your experiences so far. So thank you so much.
Pleasure.
You're very welcome.
So thanks to the audience too for these great questions. I just want to remind you that this webinar series is part of a larger project, which will be formally launching in the next few weeks. We're kicking it off with a request for proposals that's expected in this summer. It will be asking or looking for multidisciplinary teams will design solutions for low-rise residential buildings in BC's Lower Mainland or the Capital Regional District. And it will involve a 6-month exploration lab with support from climate, energy, and health experts to really kind of dive deeper into some of the issues that we've been able to talk about today. If you intend to answer the RFP or you want others to know about how your company can contribute to a proposal, we invite you to log your information at pembina.org/reframed. We think that, you know, this is really a team effort, and we're looking to draw experts from all groups, including architects and building science and mechanical engineers, contractors, retrofitters, manufacturers, you know, modeling and digital capture, the monitoring and control equipment specialists. All these folks need to be involved from the beginning of these projects. The information that you log into the Reframed page will be published online so that we can have others in the industry discover some of the amazing innovations and ideas that you're coming out with. And you know, maybe they haven't been able to hear about them before. This is a place where we can start to discover each other. As you might have gathered from today's discussion, we're really particularly interested in retrofit solutions that integrate technologies such as prefabricated panel solutions. We're looking for high efficiency and low carbon mechanical systems. We're looking for roofing solutions that integrate on-site renewable. You know, we need to be considering storage and/or thermal generation. Seismic upgrades are part of the solution, climate adaptation measures, and we need to be thinking about system controls and performance monitoring. So if you see yourselves with innovations in those fields and you understand your role in this retrofit space, please do log your information at the Reframed page, and so that others can learn about your work. And towards that step of integration, our next webinar will be diving into heat pumps and their role in retrofits. We hope that you enjoyed this webinar and that we'll see you at the next one. It's May 27th, and you can sign up for that one at the Reframed Tech Series page on pembina.org. We'll be following up with other webinars such as covering embodied carbon, which we had a short discussion about today, and also looking at climate adaptation measures and considering some other subjects as we roll these out. So thanks so much for joining us. If you have a question about Reframed or anything else that Pembina is up to, then or if you're interested in learning how your company can get involved, then please visit us at pembina.org/reframed or email us at reframed@pembina.org, or you can just email any one of us directly. Thank you so much.
Cool. Thank you.
Thanks, everyone.
Thanks, everyone.
Thank you. Bye.